I'm deeply honored that you all showed up at this ungodly hour. I must say, Eliezer rocks. Look at that. I still don't know how we did it. This is a real blackboard, you know. I'm in love. It's amazing. Okay. So yesterday, that makes that god-awful noise, though. You know?
You want to perfect?
Yesterday, we talked about conformal symmetry and twistor variables. Already we see the hints of something that we're going to see more and more of in the rest of the lectures. That the fact that the conformal symmetry is SL4, all these SLs, the fact that the natural variables live in projective spaces, the fact that the symmetries are just linear transformations, is highly suggestive of planes showing up all over the place. Okay? And so we see this in the conformal symmetry and dual conformal symmetry, and we'll see it when we start talking about Grassmannians. But there's really something very simply linear algebraic going on here. The only transformations we're talking about are just general linear transformations, okay, or SL4 with determinant 1 for the case of the symmetry, of conformal symmetry. And again, this is one of the reasons we're spending a little bit of time talking about the variables that make the action of these symmetries as simple as possible. So yesterday we talked about twistor variables in space-time. So we have the basic correspondence that a null ray in space-time associated with the equation mu a dot minus x a dot lambda equals 0. So this was space-time and twistor space. So grouping the lambda and the mu into this four-dimensional vector, which are equivalent up to a rescaling. So C lives in CP3. So the first part of the correspondence was that a point in twistor space is associated with a null ray in space-time, and the second part of a basic part of the correspondence is that a line in twistor space with two representative points on it, let's say A and B, corresponds to a point in space-time, okay? X that's associated with A and B. Okay. And the beautiful thing is that the conformal group, the conformal symmetry, is just SL4 on the Z's. Now, that's what conformal transformations look like on space-time variables. And in a moment, when we talk about the dual space-time that's associated with dual conformal transformations, we'll literally be using these space-time variables. But for the moment, let's just talk about ordinary space-time, our space-time. Okay? And this is great. It's great for talking about conformal transformations acting on coordinates. But if we're interested in scattering amplitudes, we're perhaps more interested in conformal transformations acting on amplitudes, so acting on momenta, or better yet, acting on lambdas and lambda tildes, functions of lambdas and lambda tildes. So this is not quite that yet. Here we're talking about variables. On the left-hand side, we're talking about space-time variables that depend on points in space-time. So what we want to do is see how we get amplitudes to depend on these kind of variables on the z's, but they don't start off life being functions of x's. They start off life being functions of lambdas and lambda tildes. Okay? So the question is, how do we take a function of lambdas and lambda tildes and take it into twistor space to make it a function of lambdas and mu's, for example? Okay? All right. So in order to see that, let's just talk about the simplest thing before talking about interactions or amplitudes or anything. Let's just see what the simplest object is, which is a plane wave. Or better yet, let's talk about a general solution of the wave equation in 4 dimensions. Yes, Brock?
A question about the definition of Z.
Yes.
I noticed that while usually we assign dimensions to quantities in physics, you didn't assign dimensions to Z.
Yes.
There are actually 2 components, the lambda
Yes.
and the mu, and we
That's
can
right.
only infer some relation between their dimensions.
That's right. That's right.
There's no dimension so far, and in particular, they have different dimensions.
Yeah, that's the
product kind of dimension.
Right.
Which reminds us of maybe phase space, not an ordinary phase.
Yeah, that's perfectly fine. If you like, you can put a mass parameter there by hand to soak up the units. And the reason it doesn't matter is that amongst the conformal symmetry is just scale invariance. And so you can rescale that mass parameter to be anything you like because things are conformally invariant. Okay?
You cannot make both of them dimensionless.
No, I'm not making them dimensionless. No, I'm saying I put a mass parameter in to soak up the dimensions, and because of scale invariance, I can scale that to be anything I like. So that's, you're right. So I should put a mass parameter in if I want to demand that the 2 components have the same units. But the theory is scale invariant. So I'm not really breaking conformal symmetry by doing that, because under scale transformations, I can send that mass parameter to anything I like. Okay, so now what we're about to do is an exercise that you have all done at some point and seen in simple graduate courses. We're just going to write down a solution to the wave equation. Okay. So how do I do it? Well, I want to write it as a sum over plane waves with some maybe f of p, right? But for this to be a solution of the wave equation, I should only integrate over the p's that satisfy p squared equals 0, right? So I'm going to put a delta of p squared here. So that's a general solution of the wave equation. If I hand you some f of p, you can build a general solution of the wave equation this way. Now, in courses, what we normally do is we immediately rewrite this guy. This is what we normally call the Lorentz invariant phase space. Of course, normally we put some energy positivity condition. I'm ignoring those niceties here. So forget about energy positivity. But what we do is we immediately rewrite this as something like d cubed p over magnitude of p. Right? That's perfectly fine. It's Lorentz invariant by construction. That's where it comes from. But it is annoying that, that to write down this nice Lorentz invariant solution to a massless wave equation, we immediately pick a frame. And we break manifest Lorentz invariance. Okay? So you have a choice. Either you write it this way, which is Lorentz invariant, but has these redundant variables. P is constrained. Or you write it as something non-redundant, but you break Lorentz invariance. The question is there a nicer way of writing this, which doesn't break Lorentz invariance? And of course, there is a nicer way of writing it. And let me tell you what that is. We want to take advantage of the fact that we know what p looks like on the support of p squared equals 0. P looks like lambda lambda tilde. Okay? So we can write p a dot as lambda tilde a dot on the support of momentum conservation of p squared equals 0, right? So clearly, this sucker should be written in terms of lambdas and lambda tildes. Okay? Now, what could it be? What do you think it is? Dumbest thing almost always works. And if it doesn't work, you've learned something, and then you do the second dumbest thing. Okay? So okay, that's it. So we did the dumbest thing. Is that right? What's a reason to be suspicious that it's not quite right? It's a 4-dimensional and not 3-dimensional, right? But of course, that's perfectly fine. That's just going right back here. We know the lambdas and lambda tildes are not well defined, right? Lambdas and lambda tildes are only defined up to rescaling. Lambda goes to t lambda, lambda tilde goes to T inverse lambda tilde. This is a GL1, if you like. Okay? It is a GL1. And so, maybe when Zvi talked about spinor helicity variables, it looks like this fantastic thing that you go from having this constrained vector with p squared equals 0 to having unconstrained values, lambdas and lambda tildes that automatically build a null vector. But then you're like, oh crap, but it's still not non-redundant because we have this rescaling that we can do on lambda and lambda tilde. But that oh crap is actually great because that's the little group. That is the action of the little group. That's how the little group is reflected in these variables. So instead of thinking about a p, which is constrained with p squared equals 0, you instead think about lambda and lambda tilde up to this GL1. Okay? And that is the completely invariant way of talking about what p is. And that's actually, so if I write this out now, d4p, delta of p squared, is equal to d squared lambda tilde modulo GL1. Okay. So that's the invariant way of writing without picking a frame. This is the invariant way of writing what this d-ellipse is, what this Lorentz invariant phase space integral is. Now, I'm going to write these kind of things all over the place from now on. Okay? So, in other words, you look at this measure, you see it has this invariance, and we just want to mod out by it. Yes?
And why it's better than the redundancy we had before?
It's better than the redundancy that we had, beforehand we had constrained variables. It's not a redundancy. Before we had 4 variables with a constraint. Now we have 4 variables with a redundancy, right? But that redundancy is very useful because it encodes it tells you what the helicities of the particles are. Okay, so beforehand we had constrained variables. Now we have variables with a redundancy, and it's even a useful redundancy. Okay. All right. So, but let's just get this out of the way right now. Super duper officially, how would you mod out by that? You maybe do some Fadeev pop-off thing. You put 1 equals something and so on. It's all irrelevant. You can do it that way if you want. Knock yourself out and enjoy a half hour of manipulating dumb expressions. Here's what it is in practice. Okay? What it is in practice is just that I can always use this symmetry, this redundancy, to, for example, put lambda equals 1z. And lambda tilde would then be a general xy. Okay? Say. Or I could put that 1 anywhere else that I like. Okay? But then d squared lambda tilde over GL1 is equal to nothing other than dz dx dy. Exactly what you would think. Okay? All right. Okay, so now we're going to go back to our solution of the wave equation. I hope it's okay I'm erasing on the same board. I don't want to use the other board. So, okay. Can you get the, tomorrow, maybe?
Get offended.
Well, it can. All right. So let's go back now. And so now we've written this in a slightly nicer way as d squared lambda tilde over GL1. This f is now a function of lambda and lambda tilde. And it's e to the I lambda tilde x. Okay. Something else I should have mentioned is when we write something like this down, and when there's many variables that are charged under a GL1, you see in this case lambda and lambda tilde were charged under this GL1 with opposite weights. I'm going to sometimes write this like d squared lambda, for example, d squared lambda tilde over GL1. Or the other way around. I can put the GL1 on any one of them that I like. Mentally, you should think of it as that, in this case, it's this guy where I gauge fix the top component to be 1. Okay, or vice versa. But we can move these GL1s around and put them on any one of the variables which are charged under the under this under the rescaling. Okay. I should also mention that just if you're being sticklers about it, this I'll put here because I'm not going to use it a lot more. But when we write something like, let's say, d squared lambda over GL1, and we say lambda is equal to 1z, okay? If lambda equals 1z, then this is equal to just dz, okay? But there's also a more invariant, I mean, here I've chosen some coordinates, and in those coordinates I'm writing it like that, okay? There is a more invariant, really directly invariant way of talking about it. This is a natural measure just on a CP1, okay? The lambda as a two-dimensional vector modulo GL1 parameterizes a point on CP1, which is just the complex plane here. This is coordinates on, one part of the CP1 that doesn't cover the North Pole, for example, okay? But I can write this in a completely invariant way if I like, as lambda d lambda, okay? You see, we know it's really, when I say d squared lambda mod GL1, I'm turning it into a 1 form. That's the whole point, right? What is that 1 form? That 1 form is actually equal to this object, lambda d lambda, where these are being contracted with the epsilon symbol now. Every time I put something in angle brackets, are being contracted with the natural epsilon symbol. And this way of writing it is very nice. If you now put any coordinates you want on the CP1, and you shove it into this formula, you'll get the correct measure. Okay? In particular, this guy is 1z epsilon 0 dz, which is just dz. Okay? Right? So you'll sometimes see formulas like that. And in general, on a CP, on a Pn minus 1, what you might call dn, I don't know, dnx modulo GL1 is nothing other than x dx dx contracted with each other n minus 1 times. Which is, again, nothing other than saying in any coordinate chart, I could put x equals 1 here, and then x2 up to xn, and it turns into dx2 up to dxn. Okay? That's just a side comment. So that's the completely gauge invariant way of writing. So this is a gauge invariant way of writing it, just modding up by the redundancy. This is a gauge invariant way of writing it. And in any specific coordinates on any chart that you want to use, it's just the most naive D of everybody. Yes?
Is it true that you can choose this particular coordinates only if your integrand is GL invariant?
Sorry? Yes, yes, that's right. That's right. Which it is, because this was a function of P. Okay? So anyway. In other words, here I'm assuming that this is a scalar. So it doesn't have any weights. If I wrote something, if I wanted to write down a solution of the wave equation for a spinner or anything else, I'd put more spinner weights here. And to make up for those, I would put more lambdas and lambda tildes in front of here. But here I'm just writing down a solution to the scalar equation. OK. All right, very good. So this is actually great. Because now, for instance, I can actually, I'm just going to write down a formula for this guy. Let me, for instance, write it like this. Let me put the GL1 on the lambda. And now, well, what is this? This is now I'm just doing the integral over all the lambda tildes, d squared lambda tilde of this guy. E to the I something lambda tilde. Well, that's just a Fourier transform of f with respect to lambda tilde. Right? So what do I get? I get the Fourier transform of f as a function of lambda. And what is the Fourier conjugate variable? The Fourier conjugate variable I can call mu, which is equal to x lambda. Okay? I should have said something, and you should have stopped me. Here I'm talking about Fourier transforms and everything. In doing that, I'm assuming these variables are real. Okay? In other words, I'm assuming that lambda and lambda tilde are independent real variables, just for simplicity of discussion here, right? So that strictly corresponds to working in general. I said lambdas and lambda tildes are complex. So if they're totally general and complex, we're just dealing with complexified Minkowski space. If lambda tilde is the complex conjugate of lambda, we're dealing with real Minkowski space. If lambda and lambda tilde are independent real variables, then we're dealing with a space-time with 2, 2 signature. Okay? So strictly speaking, these manipulations are true in, and thinking of it as a Fourier transform like this is true in 2, 2 signature. Okay? But we're going to use this mostly just as a bookkeeping device for simple representation theory. Okay? So when it's convenient, we'll be dealing with these real variables and talking about Fourier transforms. But rest assured that there's a way of saying all these things that's valid in the general complex case. All right, so now I can write this more fancily if I like. This is just an integral over a CP1, so I can write this as an integral if I like. I mean, it's the same thing as I just explained. Lambda lambda tilde f of z, okay? It's a function of lambda and mu, but mu is equal to x times lambda. This is known as the Penrose transform. You see, it's very pretty. It says that to get a solution of the wave equation at a point x in space-time, you take some function that lives in twistor space. This is a function of z. This is f tilde of z. Okay? You pick a CP1, so you pick a lambda. You pick a CP1 that lives in the CP3, so you choose a lambda. You integrate around on that CP1 of this function, but it's evaluated with the mu component is equal to x times lambda. Right? And of course, mu equals x lambda was exactly the correspondence between null rays in space-time and points in twistor space. Okay? So we've discovered just in this very simple way of writing a solution of the wave equation in a slightly more invariant way, we immediately discover this construction of Penroses for writing down solutions of the massless wave equation. Okay? And at the same time, we've discovered how to go from momentum space to twistor space. Okay? After all, this thing would encode the wave function, for example, of the external momentum states. Okay? So the amplitudes are functions of lambdas and lambda tildes. The way to take them into twistor space is to Fourier transform, let's say, the lambda tildes. Okay, so if you Fourier transform the amplitude as a function of the lambda tildes, you'll get a function of lambdas and mu's, and so that's giving you a function that lives in twistor space. Okay? So the path from momentum space, the path from space-time to twistor space is just algebraic and is the simple incidence relations, mu equals x lambda and backwards and forwards. The path from momentum space into twistor space is a half Fourier transform. Okay? You either transform the lambdas or the lambda tildes. Sorry. Now, here I chose to transform the lambda tildes. I could have also moved the GL1 over on the other guy and transformed the lambdas. So there's actually two things that I could do. Okay? And what does that correspond to? Let's say I had done it the other way. I should do that because I'm actually going to use these conjugate twistor variables just as a convention throughout the rest of the lectures. But if I did that, what I would get is exactly the same thing. But instead of getting mu and lambda, instead of getting lambda and mu, I would get mu tilde and lambda tilde. And now the incidence relation would be mu tilde minus x lambda tilde equals 0. Okay? Where mu tilde now has an A index. This is A dot, lambda tilde A dot equals 0. Okay? So there's two naturally conjugate things that I can do. Remember, lambda and lambda tilde are related by parity. Okay? So exchanging lambda and lambda tilde is parity. And so Fourier transforming with respect to lambda tilde, going to this space, these are the z's. And we said by convention, let's say they have an upstairs SL4 index. So I runs from 1 to 4 as an SL4 index. So these things by convention are called W's. They have a downstairs SL4 index. Okay? So what is the relationship geometrically between z's and w's? If z is a point in twistor space, Z is a point in CP3. What does W correspond to geometrically? Remember, the only tensor that we have is the epsilon symbol. Okay? So, raising and lowering indices, or upstairs and downstairs indices, well, so geometrically, let's say I want to specify a plane in CP3. Okay? So literally, here, a plane in CP3 is given by the equation Wi Zi equals 0. Okay? So all the solutions of this as a function of Z's lie on some plane. So a plane is associated, the data of a plane is associated with something with an upstairs index. Okay? This is nothing other than just good old-fashioned Poincare duality. Okay? So we have a duality between points and planes. Okay? And in CP3, lines go into each other. Lines go into lines. All right. Very good. So that's how we go into a twistor space. Now, I could at this point actually take some simple amplitudes and Fourier transform them for you, just so you see what they look like, because they look amazingly simple and beautiful in twistor space. But I'm going to postpone it for a second because it's going to be much easier to think about all of these things after we have a tiny bit of this. Grassmannian way of representing these things under our belt. It's going to be much, much easier to think about the geometry. We won't have to do any actual work. All right. Oh, so let me say a final thing. Here we've been talking about just the conformal symmetry. Here we've just been talking about conformal symmetry, SL4. But the superconformal symmetry is SL4/4. And all we do is we adjoin, so we can talk about curly Z's, which are Z up here, and we adjoin 4 fermionic variables to them as well. Okay? So the A to I are 4 fermionic variables, or similarly the W's are curly W is W and some eta tildes. So this I is an SU4 R symmetry index. Okay, so there's 4 of these things as well. There's 4 of these things. So super amplitudes are functions. Sorry? This is with n equals 4. Yeah. Yes, of course. Yeah. But I'm talking about the maximum case. Yeah. Okay. So super amplitudes are functions of, even before going to a twistor space, super amplitudes are functions of lambdas, lambda tildes, so super amplitude Mn is a function of lambda, lambda tilde, and by convention, I will be using the eta tilde variables. Okay? Now, let me just tell you what these things are. So ordinarily, we label the external states by helicities, right? Plus, minus 1. But that's a very unnatural thing to do when the theory is supersymmetric. It's particularly unnatural. And something different is much more natural because especially maximal supersymmetry unifies all the helicities into one multiplet. Okay? So that's a fantastic thing because you don't have to label in an annoying way the amplitude with pluses and minuses corresponding to the helicities of the particles. Okay? But in fact, the most natural thing to do is to label the external states. You try to diagonalize as many of the symmetries as you can. That's, after all, why we talk about momenta, because it diagonalizes as much as Poincare as we can. But since we have Q and Q tilde, they don't commute, but we can diagonalize one or the other. Okay? So we can talk about eigenstates of Q or eigenstates of Q tilde. And those are Grassman coherent states, a particular linear combination of the different helicities, which diagonalize one or the other. Here I'm choosing the eta tildes that diagonalize one of them. I forget which one it is with my conventions. But what it is explicitly in terms of states is a plus helicity gluon plus eta tilde I, the plus a half helicity fermions, plus 1/2 factorial eta tilde I, eta tilde j, the scalars ij, plus 1/3 factorial eta tilde I, eta tilde j, eta tilde k, minus a half ijk, plus 1/4 factorial eta tilde I, eta tilde j, eta tilde k, eta tilde l, times the negative helicity gluon ijkl. Okay? Of course, this thing is, there's only, because the eta tilde is anti-commute, this thing is just proportional to epsilon ijkl, so there's only one term there. The 4 factorial kills it, so that's the negative helicity state. There's only a one term, there's 4 terms, there's 6 terms here, 4 terms here, and 1 term there. Okay? So this state is a particular combination of all the helicities, of all the different helicity states. And if you want to extract a particular component, if you so desire, well, it's just trivial. You just project it out of the state however you like. Okay? So for instance, I don't know if Zvi wrote this down already, but let me write down what the MHV super are. And so one last bit of notation is we're going to talk about amplitudes as a function, mn of lambda, lambda tilde, and eta tilde. We're going to write as a sum over n and k of mn k of lambda, lambda tilde, and eta tilde, where k, you see, these are Grassman variables, so whatever this function is a polynomial in the eta tildes. Because there's an SU4 R symmetry, these eta tildes, the only thing that's contracting them is the epsilon symbol. So the eta tildes come in multiples of 4. Either no eta tildes, 4 eta tildes, 8 eta tildes, and so on. Okay? So MNK is just that sector that contains 4k eta tildes. Okay? And what it physically corresponds to is MNK, if you look at the component amplitudes, for example, that have only gluons, MNK are the ones where k of the gluons have negative helicity and the remainder have positive helicity. Okay? So k counts the number of negative helicity gluons. It's an extremely simple exercise, perhaps Zvi went through already, to show, for example, that just from supersymmetry alone, and it's actually just essentially trivial if you just use these eta tilde variables. Okay? Use these variables, it's a 2-line argument that this amplitude vanishes if k equals 0 or k equals 1. And it vanishes if k equals n minus 1 or n. Okay? It's a very simple exercise. Okay. So the first non-trivial case is k equals 2, which corresponds to the MHV amplitudes in components where 2 are negative helicity, everyone else is positive helicity. And so let me just write that one super amplitude so you see what it looks like. For k equals 2, mn2 is equal to I'm going to write this delta function for momentum conservation, even though it's so trivial we normally don't write it down. But I'm writing it down for a reason that will become obvious. So that's what the MHV superamplitude is. Okay? You see there's momentum conservation, and there's its supersymmetric counterpart, which is a delta function involving the Grassman variables. There's a delta 2 times 4, y 2 times 4. The lambda has 2 components. There's 4 eta tildes. Okay? Now, a very beautiful thing about labeling the amplitudes in this way as functions of lambdas, lambda tildes, and eta tildes is that the cyclic symmetry that they have is completely manifest. We're labeling all the external states now in the same way. And so the Bose symmetry of the underlying amplitude, when we strip off the color factors, turns into a cyclic symmetry of this color stripped guy. So these amplitudes are cyclically symmetric. And in fact, now, however, when you look at specific helicity amplitudes, you never see that. If you look at an MHV amplitude, there's this denominator that you recognize, but there's always this numerator factor, ij to the 4th. That's fine, because I and j are the 2 guys that have negative helicity. So there should be something there that's breaking cyclicity. But it's kind of annoying because it feels like, you know, the basic object is cyclically invariant. Well, supersymmetrically, you see that it's cyclically invariant. How from here do we extract the component? Let's get the actual, component amplitudes we know and love. Let's say I want to make particles I and j have negative helicity. Okay? And everyone else have positive helicity. How do I do that? Remember, eta tilde was plus dot 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 plus eta tilde to the fourth minus. So all the guys here who are plus, I'm going to put their eta tildes to 0. Okay? And for I and j, I'm going to do integral d4 eta tilde to extract the eta tilde to the fourth component. Okay? So this is d4 eta tilde I, d4 eta tilde j of m n and 2 of this thing, right? Now I've put all the other eta tildes to 0, so this thing is delta 4 of eta tilde I, lambda I, plus eta tilde j, lambda j, and then I have the rest of the part-Taylor denominator factor, and I'm not bothering with the momentum conservation, okay? Now what is this integral? This is the Grassman integral. So what is this integral? What's the numerator? It's just ij to the fourth. That's a little exercise. So you can see the super amplitude is cyclically invariant. If you project out a particular component amplitude, you're going to break the cyclic symmetry. But of course, the object is cyclically invariant. Okay, yes?
Where's the ij to the fourth?
It's doing this integral. d4 eta tilde I, d4 eta tilde j. Okay? If you do this integral, you get ij to the fourth. How? Well, okay. You didn't hear that I said homework exercise? Each one of these things is, let's say, just for fun, that I put lambda equals a0 and lambda tilde equals 0b. Okay? All right? Then what is this delta function? It's delta 4 of eta tilde a, eta tilde j, b. Right? So what happens when I do integral d4 eta tilde I, d4 eta tilde j? This delta 4, this gives me a to the fourth, b to the fourth. The a's are upstairs because these are Grassman variables. So that delta 4 eta I is really eta tilde I to the fourth, a to the fourth. Okay? But ab to the fourth is nothing other than, oh sorry, that's lambda I and lambda j. This is obviously just ij to the fourth. Okay? Of course you could do it more invariantly, but all right. Is that clear? Very good. So the super twistor variables are just, we just have z's and etas, and the super conformal group is SL4/4. And that means that what are the generators? Well, they're just z ddz, z dd eta, eta ddz, eta dd eta. Okay? So that's what SL4/4 means. Just super linear transformations. Beautiful. Now, now there's a particularly beautiful use of these, of working in twistor space. As you see, twistor space is ideally set up to talk about just the kinematics of amplitudes, right? The kinematics are as simple as possible. The conformal symmetry is manifest. But also every other question that you might ask involving on-shell objects, okay, is most naturally formulated and computed even in twistor space. So I want to talk for a second about natural things that we can do if we take two different objects. We can glue them together, for example. We can attach things to each other in lots of physically motivated ways that are literally related to generalized unitarity that I'm sure Zvi has either talked about or will talk about. But let's actually just first, even before talking about generalized unitarity, let's talk about something incredibly basic, right? let's say I have, I don't know, some amplitude on the left here and some amplitude on the right. Okay? There might be trees, there might be whatever they are, there might even be amplitudes. There are some on-shell objects that depend on the lambdas and lambda tildes. And I want to glue them together along this line. But this thing is on shell and this thing is on shell. Everything is on shell here. This is not a virtual line. Everything is on shell. So what could it possibly mean to glue two of these things together? And let me also say something very important. It's going to be more and more important as we go on. When we talk about amplitudes here, everything is included, including the delta function for momentum conservation. Okay? So every single object we're talking about has the delta function for momentum conservation and everything. We're not stripping off those things. So whatever this thing is, this thing is a function of a bunch of variables here. This thing is a function of a bunch of variables here. What could it mean to naturally glue them to each other? Well, what it could mean is that if this was a lambda and a lambda tilde, that should, let's say, be lambda negative lambda tilde. All the momenta are incoming here. So we want to impose that those things are, that the momentum is the same. So we're gluing them, right? And then the only natural thing you can do is just to integrate over the phase space of those massless particles. So that's the only natural gluing operation that we could talk about. Okay? So we could do d squared lambda tilde over GL1 of something on the left, some function on the left of the other variables and this intermediate guy, and some function on the right, these variables and the intermediate guy. Okay? So there are these natural on-shell ways of gluing things to each other. If I just do that, and I don't know, it's a tree amplitude on the left and a tree amplitude on the right, this thing is literally going to be a so-called factorization channel, right? Because I'm going to integrate over this guy, so I'm going to get something, but the final thing that I get is going to have a delta function which forces that this guy here, well, in fact, we know that the momentum here is the sum of all these guys. So when I integrate over the d squared lambda tilde, I'm just going to nail what lambda and lambda tilde are. It's in fact going to be more than that, because it's going to enforce a delta function that says that the sum of all the momenta here have to square to 0. Okay? So if I take this operation, I glue two things together, what I'm getting is the product of the guy on the left, the guy on the right, multiplied by a delta function that actually enforces that the sum of the momenta on the left squares to 0. Okay? That is a very nice and beautiful canonical object. Okay? That's in fact literally, for example, if you had a tree amplitude, as I'm sure as V discussed, as you approach one of its poles, as you approach one of the poles of this tree amplitude, what the pole looks like is exactly this. It looks like 1 over p squared, and then you have an amplitude on the left, an amplitude on the right, summed over all the helicities of the guys that run around the middle, right? The residue on that pole is literally this guy. Okay? That's what it's doing. It's a delta function that forces you to be on there of the guy on the left, the guy on the right. Okay? So this way, this on-shell way of gluing things to each other is very natural and important. Okay? Now, here normally, we also sum over all the helicities that run here. So the helicity is the sum over h and negative h. This is another very nice thing about using these supersymmetric variables. Instead of summing over helicities, all you do is you integrate over the eta tilde. So I also put a d4 eta tilde. In other words, not only do you enforce that the lambdas and lambda tildes are equal, but you enforce that the eta tildes are equal, and you integrate over them. Yes? There's no propagator. No, absolutely not. That's really crucial. There's no propagator here. No propagator. Nope. Huh? Intermediate state. Nope. There's no propagator. It's better not be a propagator, because that would give you an infinity, because it would be 1 over p squared, and the p squared is equal to 0. This is not what it is the residue of if this was a full amplitude and it was factorizing in this way, it really gives you the residue. Instead of the propagator, it's putting a delta function. It says that this thing only makes sense when the sum of all the external p's squared is 0. Okay? And then the rest is the product of the guy on the left and the guy on the right. So you can do this, and we can, in this way, we can on-shell glue lots of guys into each other. Right? We take little objects and glue them into bigger objects. And there's something important about the suite of objects that we get in this way. I'll talk about it a little bit more in a second. For example, so this corresponds to a factorization. Okay? Let's draw another picture. This is maybe a little more familiar. What is that? That's literally a unitarity cut. Okay? Because now what I'm doing is I'm doing the d-ellipse over the this d squared lambda tilde over that guy. Okay? And the resulting object now just gives me a this is the standard unitarity cut. Okay? For example, this object, if the momenta are generic on the outside, it vanishes. It has a delta function in it that enforces that the sum of all these guys squares to 0. This thing does not vanish for generic external momenta. It's the unitarity cut. But the way to write the unitarity cut is like this, right? It's literally doing one of these. I write down the guy on the left, the guy on the right, and I write down these integrals for each one of the things on both sides. Okay? All right. Now this whole operation looks more natural in twistor space. Okay? And it's also very natural here, but this is just a trivial exercise in Fourier transformology, so I won't do it, but I'll just tell you what the answer is. It's so obvious that you'll believe it.
So
yes?
Are we imposed that the intermediate plane is on shell, right?
Everything is on shell. Everything is always on shell.
Finally, we would like to make computations also when it's off shell.
No, remember. Huh? That's right. We'll do other things. We'll add z variables. That's right. Well, physically, no. Physically, that's in your head. That's if you're calculating Feynman diagrams. These are not Feynman diagrams, right? That's right. Yeah. No. Exactly. Precisely. Exactly. That's right. Exactly. So in doing this, we're going to get a whole suite of objects, which are the natural ways of gluing things to each other on shell in all possible ways. This information allows us to construct the entire amplitude. Trees, loops, everything, okay? But we're going to start off talking about this set of very physical objects that we get from gluing things to each other, which are called leading singularities, okay? And I'll speak a little bit more about what their interpretation is. But I just want to say what this thing is in twistor space. It's exactly what you'd expect. We now have a twistor variable here, w. Let's say another twistor variable here, w. And it's now just the integral d4/4w over GL1 of m left of w, m right of w. Okay? So the d4w over GL1 is just the natural projective integral over CP3. I should have maybe stressed this before. Just a very simple point, but our GL1 redundancy, lambda goes to T lambda, lambda inverse, lambda tilde goes to T inverse lambda tilde, which is helicity. That's always annoying because the fact that lambda goes one way and lambda tilde goes the other way means that you can't quite talk about them projectively. Maybe talk about lambdas projectively, but then you can't lambda tildes and vice versa. Once we go into twistor space, it's just w goes to tw, right? So now they're beautiful projective variables. And furthermore, the weights are such that if we're talking about Yang-Mills amplitudes, super Yang-Mills amplitudes, all the objects we're talking about have weight 0. Okay? So they're really things that live in the projective space in CP3. So we're going to see this a lot. d4/4, so it's d4w mod GL1. So that's the natural projective measure on CP3. And the /4, the other ones are just the d4 eta tilde. Okay, so W was these bosonic W and the eta tildes. And so that's just D4W mod GL1 D4 eta tilde. So in other words, if you just integrate over twistor space, drawing things that look like Feynman diagrams in twistor space and integrating over the intermediate lines, what they're doing is computing the on-shell way of gluing things into each other back in momentum space. Okay? Yes?
Where did the sign differences appear?
Oh, it didn't. Although it doesn't matter because these things are invariant under W goes to TW for any T. So, huh? No. Now in terms of the W's, it turns into all of them. That's the slightly non-trivial part of the Fourier transformology. But yeah, so that's right. Before there was a relative sign. Now it just sits in front of all of them, and then it doesn't matter. Okay. So that's why it's literally just integrating over twistor space and just identifying points. Okay. So let me just stress this again. So if you draw a picture like this. If you draw a picture like this where you have a bunch of guys, these are just various on-shell objects. And we can even make it look like a loop. Okay? If you draw this picture, you put W's on the intermediate lines, W, W prime, W double prime, W triple prime, and you just do integral D4/4 W over GL1 over all of them, of all the functions, F1, F2, okay? What this thing is doing is just computing the on-shell gluing of all of these guys beautifully back in, if you want to think about it in momentum space. What it's doing is on-shell gluing them all into each other. Yes?
So why do you emphasize the factorization channels? I mean, especially the one particle exchange, if you can apply it also to...
No, I'm not. I just gave that as one example. No, you can do anything you want. So we just did I just showed you a unitarity cut. You can make a 12-loop diagram if you want. Okay? The point is that you can draw diagrams that look like multi-loop, complicated diagrams of this sort. And these diagrams make sense on shell. They make sense as on-shell objects, where instead of thinking about all those lines as being off-shell things that we're integrating, you think of them as all being on-shell and you're integrating over their phase space. Okay? So there's two different, they look similar, they look like Feynman diagrams, but they're not. They're on-shell avatars of Feynman diagrams. Okay? They're totally well-defined. They're totally well-defined data that's just gluing things together on-shell. Okay? Yes? I'm going to give you their physical interpretation in just a moment, but yes.
That's only planar also.
No, here it has nothing to do with planarity. It's just the board is planar, so we can, yeah, we can draw. Yeah, we can draw, things that Zvi loves. Okay, draw, no problem. What I'm talking about here has nothing to do with planarity. This is all kinematics. Okay, so gluing things in the obvious way in twistor space is just gluing them on shell. All right? Yes.
Doesn't the integral in twistor space already contains the modulation by GL1?
Sorry?
Doesn't the integral D4/4 already contain the GL1 modulation?
What do you mean modulation?
Dividing by GL1. Isn't it somehow contained in the...
Sure. No, of course. I mean, so that's why I said. I'm just a simple guy, so I like to... I like to be as explicit as I can, and I like to always think about these variables as four-dimensional variables up to a GL1. You could just say they're integrals over CP3/4, and then you don't have to say a GL1, of course. And then we can even write the measure as W, DW, 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 D4 eta tilde, and that's a super-duper official measure on CP3/4, and you should be very proud of yourself. So that's, okay? Yes?
What is the dual conformal invariance in this language?
I'm going to come to that in a second. So we're talking about just about the ordinary conformal invariance. That's the rest of the lecture. Okay. Okay. But let me now tell you what the interpretation of these things are. So you see, it looks like, let me just be a little loose for a second. If I draw something like this, it looks like as if I'm doing an integral d4p, but instead of having 1 over p squareds for the propagators, I have delta of p squareds for the propagators. Okay? That's what it looks like. Now, let's think for a second about adding up all the Feynman diagrams. Okay? So we get something, and if we're really adding up Feynman diagrams now, then we get a function, we get some loop integrand, something we've got to integrate to get the final result. Okay? I want to emphasize this here much. The notion of a loop integrand is really not a precisely defined notion for non-planar theories. So it looks like you can just take all the Feynman diagrams and put them under a single d4L integral. But you can't, because the notion of what L is different for that diagram and that diagram and that diagram. There's no natural origin for momentum space. Okay? When it's planar, it turns out there is a natural origin, and you can define a well-defined notion of an integrand, and that's very useful. But it's probably not going to be critical. We're probably going to be able to figure things out even without that crutch. Anyway, let's, for simplicity, talk about the case where there is a well-defined integrand. Okay? So we have this integrand. So I sum up all the Feynman diagrams. There's some integrand. It's a complicated function of a whole bunch of loop momentum variables. And what Feynman instructs you to do to get the final answer that has polylogs and complicated things in it is to literally do the integral. You do it from minus infinity. You do it over all space-time. L equals minus infinity to infinity. Okay? That's fine. But it's also, you know, it's slightly ill-defined. It has infrared divergences, blah, blah, blah. Okay, but that's fine. But there's another set of well-defined integrals that you could do. And in fact, if you handed this complicated, it's a complicated rational function, right? It's a complicated rational function, polynomials in momenta and stuff like that. If you handed it to a mathematician, they would say, these polylogs are horrible and too much work. I'm going to try to do some simpler integrals. And you can do simpler integrals. What you can do is, instead of evaluating the integral from minus infinity to infinity, you can find other natural contours of integration. What are other natural contours of integration? They compute residues. See, this is a rational function, so it has all sorts of poles everywhere. And instead of doing the whole integral, you can actually compute the residues at all the places where those poles occur. Okay? Now, you might think this is a good strategy, because we know from many simple examples that once you have all the residues under control, then you can build up and start figuring out what the whole answer is, right? But even quite apart from that, it's data. It's really things about the amplitude which are perfectly well defined. And this is another nice feature that they have, is that these things are not infrared divergent. They're little compact cycles of integration, and they compute residues. Better than that, they're not even integrals. They're just residues. So you compute them just by, you have to solve a bunch of polynomial equations to put all these various p squareds, all the various internal, the only poles that we have are 1 over p squareds for all the propagators, so you've got to put a bunch of them to 0. But then you just zoom in that neighborhood, and you just compute a little Jacobian, and you pick up the residue. Okay? So these residues of the loop integral, of the loop integrand, which, again, are just doing the actual loop integral on a different contours of integration. Different natural contours of integration that pick up the singularities. These have a name, and they're called leading singularities. Okay? How do you compute leading singularities? These guys. Okay? Let's think about it just at one loop for a second. You have a d4L integral, right? So there's 4 variables, L0, L1, L2, L3, d4L. So if you're going to try to find a residue, you have to find sort of 4 poles, right? 4 things. You have to pick out a point in this 4-dimensional space. Okay, well, what kind of singularities can we possibly have in the integrand? Again, the only singularities we can have are when certain internal lines go on shell. In fact, we have to find a situation where 4 internal lines go on shell if we're going to try to compute a residue. So whatever the heck what would it look like, for example, with 2 internal lines going on shell? 2 internal lines going on shell. So here's one of them, and here's another one. Okay? See, this guy's on shell and that guy's on shell, right? So already, just finding a situation where two of them are on shell, there's still two integrals left to be done. Okay? But this is already a unitarity cut. If I wanted to keep going, I have to find a situation where there's 4 internal guys that are on shell. So if I'm dealing with a one-loop amplitude, it looks like this. And Zvi probably talked about that as well. Okay? In other words, I find a pole, a leading singularity, for every way of subdividing the external particles into 4 sets. Okay? And such that I then join them here with that being on shell, that being on shell, that being on shell, that being on shell. Okay? Is that clear? Now, because those things are on shell, what is the value of this leading singularity? I mean, what is its actual, how do you actually compute it? Well, because these guys are on shell, here I was just drawing Feynman diagrams. I'm collecting all the diagrams together into the blob there, blob there, blob there, blob there. But because these guys are on shell, all of a sudden, whatever the heck this thing is must be just the tree amplitude on the left here. That tree amplitude, that tree amplitude, that tree amplitude. So to compute this leading singularity, you have to glue together tree amplitudes, 4 of them together around this corner like this. But we're gluing them together in just the way we were discussing a moment ago. Okay? Is that clear? So that's the interpretation of these diagrams. The interpretation is that you glue things to each other on shell, and has beautiful invariant data that's very closely related to actually all loops. And what these objects, a whole suite of objects, what they're computing are in fact the residues of the loop integrals rather than the loop integral themselves. Okay? In a moment, but in the next couple lectures, we'll see how this information can be used the other way to just write down the whole answer for the integrand. Okay? But I just wanted to, there's many things that are equivalent to each other, and we're going to be staring a lot of pictures like this later. So I wanted to first tell you what these pictures mean at this level already. Yes?
We have learned about that. Just for 2 questions. First one is that in one case we know that the box diagram and triangle diagram and bubble diagram. And
yes.
You just said about some box diagram, so we must say about some triangle and bubble.
Well, you see, what I'm talking about, there's 2 different things that we could be talking about. One of them is, which I'm sure Zvi talked about, is let's say you're dealing with one loop. There's a basis of integrals. There's boxes, triangles, bubbles, rational terms, and so on. Okay, that's one. And then there's many strategies for determining the coefficients of all of those guys, and that's fantastic. That's one set of questions. Okay. Here I'm just asking a different question for the moment. They're very closely related, but I'm asking a different question. I'm asking the question, what are the residues of the loop integrand? Okay? That's a question I can ask in n equals 4. It's a question I can ask in QCD. I can ask in any theory. Right? If I literally want the residue, then it's these guys. The actual literally the residue, it is these guys. There isn't a the residue associated with a triangle, because there's still an integral left to be done. Right? So the actual residue are just these guys. Now there's a separate question, which is, do these things really suffice somehow to give you the whole answer? And in a general theory, they don't. You sort of need more information. What these things, the reason they're called leading singularities is that they're, in a sense, they correspond to the most complicated part of the answer, because they physically correspond. I should maybe say a few other words physically about this. So you know that even for something simple like a bubble, it has a logarithm in it, right? Now, why does it have a logarithm? That logarithm is there because the log has a discontinuity, right? It has a branch cut. And you know that the jump across the branch cut is being computed by the optical theorem by unitarity, right? So just getting a discontinuity in the actual final answer, which has a log in this case, is related to cutting 2 propagators in the one loop diagram. This guy is cutting 4 propagators, and it corresponds to the fact that these one loop amplitudes have dilogarithms in them. So you can cut twice. Dilogarithm, it has a branch cut. You go around the branch cut, it has a discontinuity. That discontinuity is a logarithm. The discontinuity itself has a discontinuity. Okay? And so you can keep taking discontinuities until you get nothing. Right? So these leading singularities, the reason they're called leading is that they're associated with, and you actually recognize them if someone hands you the amplitudes. You see some dilog, but then it has a coefficient in front of it. This is the coefficient in front of it. The leading singularity is the coefficient in front of the dilog. Okay? Now, it is an interesting fact in n equals 4 that we only have these most complicated pieces of the answer with the highest transcendentality objects, the ones that you can cut the maximum number of times, and there aren't lower ones. In QCD and in other theories, you also get lower ones. Okay? And so, yeah. No, it has nothing to do with planarity. This has nothing to do with planarity. Okay? Yeah. Yes. Yeah. Well, I mean, it's not proven, but it's very likely true. Yeah. But I really want to say that these things, all of these objects, are totally well defined in any theory. This is the kind of on-shell, natural on-shell data associated with any theory. How effectively you can use them to build up the whole answer is another question, right? But Zvi and friends have used them massively effectively. These and closely related objects to compute things in QCD as well. Okay? But for the moment, I just want to keep things conceptually a little clean. If you want to just talk about gluing things on shell, this is how you do it. It's interpreted as singularities of the loop integrand, and it's beautifully computed in twistor space. In fact, if you drew what look like Feynman diagrams in twistor space, what you're really computing are these on-shell gluing things with each other. Okay? Yes?
So from these objects, which are, as you say, volume-like, so you can reconstruct the amplitude up to rational pairs, and I presume that rational pairs don't exist in any.
That's right.
But enough to compute the integral, because the integral will diverge, so you need to come up with some regular
yes, right. Right. Yes, it is because there are very natural regularization procedures that are purely 4-dimensional. You go out along the Higgs branch, and it's incredibly simple to do. I may mention that a little bit. Yeah. Yeah. In fact, the main use of dim-reg, the main great thing about it is that it lets you deal with UV and IR at the same time. In theories that don't have UV divergences, totally irrelevant. You just go out along the Higgs branch. It's very easy to do. You never have to leave 4 dimensions. Great. Okay. Yes.
This the validity of this algorithm. Previously, you showed that it reproduces a Taylor Park formula, but
yes.
You had to do Feynman diagram.
Yes.
In general, I mean, you didn't start from a Lagrangian.
Yes, yes.
You give some algorithm. So how would you know that?
Oh, sorry, we haven't. Sorry, so far we haven't talked about any algorithm or anything. I'm just telling you this is all still kinematics. Okay, yeah. We're going to be moving towards it. Okay, to cut a long story short, it's possible to, roughly speaking, BCFW at tree level and at loop level kind of acts as a halfway meeting point between the usual way of doing field theory on one side and a dual way of doing it on the other side. Okay? You end up reproducing the same formulas, but you interpret them in totally different ways. On the one hand, we can derive them from field theory, so we know that they're true. Okay? The fact that they're true relies on all sorts of remarkable things. Things vanish at infinity, and there's all sorts of arguments that you got to make, but it's true. But then you see that the objects that you get have a totally different interpretation in terms of these other objects that we're talking about. And in fact, they have such a natural interpretation that once you start thinking about them from this other point of view, you start getting used to how inevitable this construction is. Okay? So that's something that we'll see a little later. But it's not that's why we're on solid ground, because we can really derive everything from good old-fashioned field theory from one side. Okay? We can derive all these things. It's just that the form of the objects we get have so many remarkable and mysterious properties that become totally obvious when you think about them from a second point of view. Okay. All right. So in fact, so I told you that every single thing. So far, I was talking about just general blobs there. Okay. Now I'm going to argue that actually the most general thing that we can talk about and should talk about is that we can blow all these blobs up so that the only things that we're doing are actually gluing together 3 particle amplitudes. So the basic amplitudes in Yang-Mills or super Yang-Mills are the 3-particle amplitudes. I'm sure Zvi talked about the 3-particle amplitudes. Okay? And there's 2 kinds of them. In components, there's the plus plus minus and the minus minus plus. And supersymmetrically, there's one with k equals 1 and with k equals 2. Okay? So the MHV and MHV bar. Okay? So one of them I will denote with a black vertex k equals 1. One of them I'll denote with a white vertex k equals 2. Okay. We'll write down explicit expressions for them in a second. Again, the explicit expressions will look at, everything will look nicer when we introduce a little bit of this Grassmannian notation. So the most general leading singularity can be drawn as a diagram, which is a trivalent diagram built out of these black and white vertices and glued with each other. Okay? Why is that? Well, remember that we started off with, for example, even at one loop, we said we had a whole tree amplitude here, and a tree amplitude, and a tree amplitude, and a tree amplitude, right? But each one of those tree amplitudes, in turn, we can compute using the BCFW recursion relations. And recursively, we can blow them all down to be being built out of 3-particle amplitudes. That's the whole point. Okay? So every blob, everywhere, everything you have can be blown down into things that are gluing together black and white 3-point functions. And then at 2 loops, it all recursively has the same property. So the most general thing that we talk about, the most general leading singularities that we talk about are actually just gluing together black and white vertices in trivalent diagrams. That's true whether the theory is planar or not. In the planar limit, the diagram should be planar. Okay? Okay? No, there's no chirality here, remember? Because everything is supersymmetric. Everything is being done supersymmetrically. So it's just black and white. That's it. Okay? Now let me actually show you a little explicitly what this looks like. You see, once you start drawing these pictures, you don't ever have to actually touch explicit expressions. Okay? So let's do BCFW. Let's, for example, compute, and let me show you what the 4-particle tree amplitude looks like in this language. Okay? How do I get the 4-particle tree amplitude? Remember, the whole logic of BCFW is that I construct in knowing the poles of those amplitudes. So I know what it looks like on a factorization channel. The factorization has a 3-particle amplitude on the left, a 3-particle amplitude on the right. It has to have a k equals 1 vertex on the left and a k equals 2 vertex on the right. I'll leave that as a tiny little k counting exercise for you. So this is what the factorization channel looks like. Okay. Here's particle 1, 2, 3. Oh, let me do it. 1, 2, 3, 4. Okay? Now, this thing, as I mentioned, this is a factorization channel, so it vanishes for generic momenta, right? This really forces 1 plus 2 squared to equal 0, 3 plus 4 squared to equal 0. Okay? So this is the pole in BCFW. We will now want to actually compute the actual amplitude, right? So to get the actual amplitude, the whole point was that you did this shift. You do the shift, and the shift allows you to find this pole and use it in order to compute the answer, right? So what does that look like? Well, let me just tell you what the answer is, and then BCFW in this language corresponds simply to the following. I'll do it in this case, and I'll then say it in general. You take whatever you have, and then on the 2 legs that you're deforming, 1 hat and 4 hat, okay, you just put, let's say, a white vertex on one and a black vertex on the other. That's it. Okay. In general, the term in BCFW that is normally said to be one where you have, the particle 1 is deformed here. You have this on the left and this on the right. and n is deformed there. That thing as a leading singularity diagram is literally, you take one, put a white vertex, a black vertex, okay? There's 1, n, and so on. Okay? Now, why does this make sense? So this is just, so what I'm telling you is that if you take this object and then glue a white vertex in, glue a black vertex in, literally do this computation, what you get is exactly the BCFW formula, which has that funny shift in it, and you've got to evaluate these things, and there's the 1 over p squared at the funny location. All of that is just that leading singularity computation. Okay? And it also has a very pretty interpretation. You see, here we had to shift 1 and 4. That's exactly what that little internal line is letting you do. Right? You're coming in with 1, but then there's some momentum flowing there that's shifting that to 4. That's shifting that to some 1 hat here and 4 hat here. And precisely because this thing is forcing 1 hat plus 2 squared to vanish, you're locking what that value of the momentum is to be precisely the one that makes the relevant shift happen. Okay? But once you start playing with these on-shell diagrams, any diagram that you draw that roughly looks like what it should be doing physically is the right answer automatically. And then you have to worry about Jacobians and this and computing anything carefully. It all just works out just directly from the pictures. Okay? So is that clear? Let's see how we go on from here. What is the leading singular? So it looks funny. This is, so let's draw it again. This is what the 4-particle tree amplitude is. Okay? The 4-particle tree amplitude, is this. 1, 2, 3, 4. It looks like a loop. But remember, these are leading singularity diagrams, so that's fine. Okay? So this is equal to M4 tree. Okay? Now let me just make a small comment here. You know that the 4-particle amplitude is parity invariant. Okay? But I've made a particular choice for who's a black and a white vertex here. Black and white are exchanged under parity. So there's a little identity that must be true that you can actually verify explicitly. It's not hard to verify explicitly. Just a very little identity. But it must be that this thing is equal to another picture where I just interchange white and black. Okay? At the moment, this is just a trivial little observation. It's just true. When you have a little square, you can colored white, black, you can exchange the colors. That little trivial thing is going to be the entire heart of the combinatorial argument that I'm going to tell you about tomorrow. This little basic move of changing the colors on a square is going to be crucial to the entire story that I'm going to tell you tomorrow. Okay? But for the moment, it's just a little curiosity. I just want you to notice. All right, so let's do one more thing. Let me just, for fun, show you what the 5-particle MHV tree amplitude looks like. Oh, I don't want to use that board. Okay. Well, in BCFW, what we would do is we would take the 4-particle amplitude that we computed, and then we would glue, so this is a k equals 2. We'd glue another k equals 1 vertex to this guy. This would again be 1 hat and 5 hat, let's say. But now let's do it with our new fancy way of doing things. So the new fancy way, we would draw this picture. And then we'd just glue this like so. Okay? And then we would attach a bridge here. So that operation of attaching a black-white is called adding a BCFW bridge. So we just add it like this. Dink, 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 dink. Okay? Okay? Yes.
The square is black or white?
It's black. Okay? Right?
The next one over there is
No. Remember, this is the 4-particle amplitude. I'm attaching to a k equals 1 vertex, which is black. Okay? And then I'm adding a bridge. So you see that the 5-particle MHV amplitude looks like 2 loops. And in fact, in general, it adds a loop. It adds a loop every time. Okay? But you just have to start getting used to these kind of pictures. Okay? So this is the 5-particle MHV amplitude drawn as a leading singularity diagram. Let's draw the 6-particle amplitude. But yes.
Can you please draw the original diagram that you want to calculate?
The original diagram we want to calculate would have had a 4-particle amplitude here and attached to a 3-particle amplitude here. So that's a 4-particle amplitude, k equals 2. This 3-particle amplitude, k equals 1, where this is 1, 2, 3, 4, 5, and then BCFW shifting 1 and 5. Okay? But the point is that you can do all of these things just with pictures. You just do it with pictures and you add these bridges. Now, this has actually a number of little things. Let me do one of the terms for you at 6 points. For 6 points now next to MHV. So 6 points next to MHV, well, there's a number of terms, but one of them is 2 4-point guys glued together. So this is k equals 2, k equals 2. Again, you'd have 1, 2, 3, 4, 5, 6, maybe with 1 hat and 6 hat. And there are other terms as well. So there's a term with 5 guys here, again, k equals 2, and k equals 2 here as well. Okay, 1, 2, 3, 4, 5, 6, and so on. So there's 3 terms in BCFW. And if you just stare at them as functions of lambdas and lambda tildes, if you actually do the computation, you get some rational function. And a priori, you get some function from one, some function from the other. Then you just notice at the end of the day, hey, these functions are actually the same. They're the same in the sense that you just rotate the indices, but they're the same object. You just have to relabel some of the external indices. It's not obvious ahead of time that that's going to happen, but it ends up happening. Okay? All of these things are trivial with the pictures, because the pictures look the same. Right? So, but let's just draw, this is just for fun, draw what the top one looks like. And notice also that there's no necessarily unique way of drawing these diagrams. Just already we saw even the square move means that I can draw the 4-point in a number of ways. So let me just draw one representation. So here's a 4-particle on one side. Okay, here's another one on the other side. Okay, okay, well, so then I can take this guy and just again add a bridge. Okay, and that's one way of drawing it. Okay. There are a number of other ways of drawing it as well that you can get related to this one by the square move. Okay. So this shows you that all the trees are special cases of these diagrams which are gluing together black and white vertices. But we're already seeing some hints of some interesting structure. There are many different ways of representing the same object. They differ by this little elementary identity as well as, well, perhaps, and maybe other things, although we'll see that that's really all there is. And furthermore, because trees can be represented in terms of nets like this, then we can represent everything in terms of nets like this, okay? So what we've concluded from this discussion is that there is a whole suite of objects in any quantum field theory, but n equals 4 in particular is particularly nice, the planar limit particularly simple, which are just associated with graphs. You just draw trivalent graphs with black and white vertices, as complicated as you like, and these pictures correspond to gluing them all together on shell. They correspond to physical data associated with the all-loop integrand. I should have stressed something. because these things are finite, these integrals are totally finite. We're doing the integral in little compact cycles. Because they are totally finite, these objects should know about all the symmetries of the theory that it has. And they shouldn't be obscured by infrared divergences or other issues. So these are really the things that tell you about all the symmetries. And so that's good, because we're going to see that these objects are directly conformal and dual conformal invariant. They're Yangian invariant. More than that, actually, they exhaust all Yangian invariants. And we'll have some more to say about that later as well. Okay? Okay, yes? How to pass from which?
From the form on the left to the graph with the...
Yeah, well, so we did it all recursively, right? We started just with a 4-point. So BCFW just for 4 points is that you have a k equals 2 vertex here, and a k equals 1 vertex here. And that's 1, 2, 3, 4 with hats. That's BCFW to compute the 4-point. Okay? Well, okay, k equals 2 vertex is a white by my convention. K equals 1 is black. And then I told you that the rule for the bridge is that you attach a white and a black. Tuck, tuck. Okay?
Why is it only one bridge that you have?
Sorry?
Why do you attach only one bridge?
What do you mean one? You mean why do I choose black white and not white black?
No, but you took just one pair and connected them.
Oh, that's because that's the way BCFW works. You take 2 particles and you deform them. Okay?
Two shifts?
That's right. That's right. So you pick 2 particles and you deform them via BCFW. Okay? And what I'm telling you is that graphically, in terms of these diagrams, what it corresponds to is just attaching a bridge. Now you could have asked a different question. Why don't I use white black? Why black white? And this is really the fact that non-supersymmetrically, when you talk about BCFW, it depends on helicities, and it's a little bit. I didn't talk about the supersymmetric version of BCFW. It's basically the same thing, and is actually nicer because you don't have to specify helicities. Okay, but essentially, what you have to do is you can shift the lambda, and you always have to shift lambda and lambda tilde. But you've got a choice about whether you work in the eta representation or its Fourier conjugate representation. Okay, so there's actually 2 ways, 2 BCFW shifts that you could talk about, and they're parity conjugate to each other. One of them is black-white, the other one is white-black. Okay? And to be fully complete, really what you should do, why did I put a k equals 2 on one side and the other side? I could have also put a k equals 1 on one side and a k equals 2 on the other side. Okay? And if I do that, what I would get is a picture. I would get this guy, and I attach a white there and a black there. Okay? Okay? So this is also there. But, and I'll talk about this a little more at length tomorrow. If you have any diagram, something that you're allowed to do is to take any diagram, and if you have adjacent blacks or whites, you're allowed to merge them with each other. Okay? So for example, I could merge here. Okay? And if you ever get something that looks like a bubble, it actually vanishes. Okay? So these things vanish for generic external momenta. Right? So anyway, so really, I'm always attaching a black-white bridge, and I should have all the left amplitudes on one side and all the right amplitudes on the other side. But some of them will vanish for generic external momenta. I was only drawing the ones that don't vanish for generic external momenta.
Where is the, in the ordinary field theory, the nth order perturbation theory,
yes,
you have a coefficient that grows factorially.
Right.
Where is this coming from?
Yeah, that is an interesting question, where it comes from is so you might have thought the fact that the answer is, again, you might think the fact that the answers in Feynman diagrams are complicated that's good, because we know there's supposed to be this n factorial growth. And even if you do things fancy, BCFW things and so on, you find that it's n minus 3 factorial, n minus 4, it's still factorially growing. So in what sense is there a simplicity? The sense in which there's simplicity is that even though the number of terms is actually factorially large, the number of objects is minuscule. What they are just the same object with relabeling the external indices and so on. But it's one basic object, or very few basic objects.
Pure
right. Pure combinatorics. Exactly. Exactly. Yeah. Yes? In fact, what you'll see tomorrow when I tell you that this is all coming from permutations is that in n equals 4 super Yang-Mills, for n particles, there's exactly n factorial objects, period, that you'll get super to any order, anything. There's a total of n factorial objects, one associated with every permutation. Okay? Yes?
When you go from the upper left diagram
Yes.
to the upper right,
Yes.
so I guess the one head it goes to k equal 2, and then it goes to the left.
Yeah.
So how do you decide how to label the other junction here?
Oh no, I just drew. I just started off drawing 2 4-particle. You mean why did I choose to make that black? I could have chosen to draw it another way. It wouldn't have made a difference. Okay.
So
Yeah.
here I see the meaning here.
Yes.
On the down left.
Yes.
I can see the meaning of the black and white, but in the upper right, I can't see why.
In which upper? Here?
No, no.
Yeah.
On down there.
Yes. Yes.
Here it is clear why you chose black and white. You say k equal to.
K equals 2 is white. That's right. Yeah.
And how do you choose it when you do it for the?
It's always on the bridge. If it's 1n, by convention, you always put the black on the 1 and the white on the n.
Okay, only for the bridge.
Only for the bridge. Yeah.
Okay, the others are.
Well, the others are what they are, and you have no choice. But and as I just mentioned, there are really 2 kinds of bridges, because you can do BCFW either one way or in its parity conjugate way. Okay, but you don't do both. You do one of them. Okay, so you choose to always make it black-white. Let's say, yeah.
But what's not on the bridge, like the legs 2 and 3 here?
Oh no, that's right. Here, no, they have nothing to do with it. Yeah. Look, it's really. Let me go back and draw the general situation, right? When we have this thing, so it's normally 1 hat and n hat, right? Right? It's very, very pretty, because I keep maybe mixing up the conventions, but let's say by convention, I always turn it into this. See, now there's no more hats here. That's 1 and n, right? When you normally do BCFW, there's the original external momenta, and then when you compute this damn diagram, you've got to find the shift and compute it, and right? There's no shift in this picture. That 1 and n is just 1 and n, right? But what this bridge is doing is exactly deforming the momentum of 1 to 1 hat there, and n to n hat there, okay? And first of all, why is it deforming those momenta? Because now I'm allowed to, I'm integrating over what that momentum can be. But now this thing here is a factorization channel. This thing down here only makes sense if the sum of all these momenta is squared to 0. So that's exactly what we look for at BCFW. I want to deform this momenta to a point where I find that I can put that guy on shell. That's exactly the purpose of this extra little leg there. Okay? Now, what is the white-black doing for you? The white-black in the language of BCFW is, did you choose to deform lambda and lambda tilde for 1 and n? Or did you choose to deform lambda tilde and lambda for 1 and n? Okay? So you have to make one choice. And that's it.
But still you have to do the work for the...
Yes, of course, you've got to do, but you have to do the work for all of these subparts. And so the whole thing is built up recursively. That's why I went through these little examples. So we went from 3 to 4, we got a little box. Then we went from 4 to 5, we got this little pentagon box. Okay? And we went to 6, and we get this thing that looks like it has 3 loops in it. Okay? Yes?
Can you explain why you are allowed to merge similar adjacent verses?
I'll explain that a little more tomorrow. It'll make a little more sense tomorrow. Yeah. Yes?
It looks to me like you can obtain a diagram with 6 external legs also by gluing together 2 of these 4-leg boxes completely without a bridge.
Well, yes, you can glue diagrams together lots and lots of ways. You can glue things together any way you like, and every single one of them has some meaning. I'm just telling you what the terms in the BCFW expansion of the tree amplitude look like. I'm just giving you, I'm just showing you that they look like these nets, okay? And because I just wanted to finish the story, that because we can show that the tree amplitudes can be blown apart into these nets, we can blow everything up into these nets, because then the higher leading singularities are built by gluing together tree amplitude and so on. Okay? So that's why the collection of interesting objects, on-shell objects, in any quantum field theory of this sort are associated with trivalent graphs with black and white vertices. Okay? Planar or non-planar makes no difference, but planar is going to have, of course, lots of additional structure that we'll talk about tomorrow. Okay, I was planning to also talk about momentum twistor space today, but that looks like it's not going to happen. So we'll pick that up again tomorrow. I will start with a lightning review of dual conformal invariance and momentum twistors, and then we'll talk about yes, we'll have some fun tomorrow. All right.